So we now know, as per de Moivre's theorem, that if you have a complex number in its mod arg or polar form r cis theta, and you raise it to a power n, you know that the modulus of that new complex number z to the n would be r raised to power n, and the argument would be n times by theta. So the next step along the way would be to say, well, what if I had a complex number z raised to power n, and it had this form? It had a modulus of big fat R, and it had an argument of theta. What is the original value of z going to be if I raise it to the power n and it equals this thing, this new value, this new complex number in the form r cis theta? Well, to do that, we'd basically be reversing de Moivre's theorem to work out the value of z. And to do that, we would be finding z, which represents the root of r cis pi, or phi. Which brings us to page 6 of our noties, which looks at roots of complex numbers. So we're talking about something that has the form z, a complex number but raised to the power n, equals r cis theta. Then, if we wanted to reverse that to find the value of just z, not z to the n, then to find the modulus, we take r, the modulus of the original, and we'd find the nth root of it. Now, when we use de Moivre's theorem, we take r raised to the power n, so we're basically going backwards. We're taking r as it is now and finding the nth root of it. Then cis, the argument, would be theta divided by n, for which z is raised to, and then, because of the nature of trig functions and symmetry, whatever the value of n is, that represents the number of roots of the particular complex number. And so there will be various numbers or various values for which the argument would be. We find those by taking theta divided by n. We add to that 2 pi k on n, where k could be 0, 1, 2, and all the way up to n minus 1. Now, if we include 0 and 1 and 2 all the way up to n minus 1, we will have, in fact, n values, or n values for z that we're trying to find. In other words, n roots of the complex number. Just before we go to some examples, note if zn just equals r with no cis theta following it, then theta must equal 0. Cis 0 is 0, so z to the n will just be z n is equals r cis theta. Let's apply that to this thing. Okay, I've got this complex number z squared equals 16 cis pi on 2. What is z? What's the original value when squared we get 16 cis pi on 2? Well, according to our rules that we've just spoken about in the box above, the general form of z in this case would be, okay, it's z raised to the power 2, so we want to find the square root of 16, and the argument would be the theta, which is pi on 2, okay, which is theta there, but then divided through by 2. Now this 2 that we're dividing it by is what z is raised to. It's raised to the power 2, we divide through by 2. Then we add to that 2 pi k, also divide by 2, and k can have some values, starting with 0 and 1, and all the way up to n minus 1. Now, n in this case is 2, 2 minus 1 is just 1. So the values of k that we're going to use in this case would just be 0 and 1. In fact, there's only going to be 2 values for z. The first one, z1, would be the square root of 16, which is 4. Then cis pi on 2 divided by 2, which is pi on 4, plus 2 pi k divided by 2, where k is 0, which will just be 0. So the first of our roots would be 4 cis pi on 4. 4 cis pi on 4. Now there's another root, another value for which z could be z2. That is the square root of 16, which is 4 again. Then cis pi on 2 divided by 2 again, which is again pi on 4. But then added to this one would be 2 pi k divided by 2, where k is 1. So that would be, so if k is 1, you'd have 2 pi divided by 2, which would just be pi, which would be 4 cis 5 pi on 4. Now, I've just left myself not much room here, but if on the side here I was to sketch those two roots, Z1 and Z2, on an Argand diagram. Okay, real bits down here, imaginary up here. So the Z1 would be 4 cis pi and 4, so it would have a length of 4 and an argument of 45 degrees pi and 4. So it might be something out here. So this would represent Z1. Now where is Z2 in the scheme of things? Well, if you compare Z2 to Z1, Z2 is pi, a distance of pi, or an angle of pi, an argument of pi away from that Z1, which means that it is 180 degrees away from Z1. So it is 5 pi and 4, which is over here. That is Z2. Now notice this, two roots of this equation, Z1, Z2, there's only two, and how much are they separated by? Well, they're separated by 180 degrees or pi. Of course, remembering that a revolution is 360 degrees, 360 divided by 2 will tell you how far the two roots are separated. They're separated by 180 degrees or pi. Okay, now back to 4 cis 5 pi and 4. Now 5 pi and 4, remember, is not legal. It's too far over our domain. So instead of writing 5 pi and 4, we should come back the other way and say, well, 5 pi and 4 is actually the same as negative 3 pi and 4. Remembering that 5 pi and 4 and 3 pi and 4 would make 8 pi and 4 or 2 pi, which is what we want to head towards. So instead of writing 4 cis 5 pi and 4, we should write 4 cis negative 3 pi and 4. There's the two roots of my equation. Z is 4 cis pi and 4 and 4 cis 5 pi and 4. Equally, when those two values are squared, you'd end up with 16 cis pi on 2. Now, just before we go on, so what if, back to this, I put down other values of k other than just 0 or 1? What if I put down k is equal to 2, for example? Okay, so say, for argument's sake, there was a Z3 where I'm using k is equal to 2. So again, you get the square root of 16, which is 4. We have cis 5 pi and, pi and 2 divided by 2, which is pi and 4. And then if we add to that 2 pi k on 2, where k was who, we'd get pi and 4 plus 2 pi. Now, of course, 4 cis 5 pi and 4 plus 2 pi is that original value for Z1 plus one whole revolution, which means we're basically getting back to the same value as Z1 as is Z3. So in saying that we have two roots, we don't need to go any further than k is equal to 0 or 1 in this case. When we go to values that are larger than n minus 1, we're actually repeating our same solutions again. So although I put down a Z3, we don't need it. We're just going to go with two roots, Z1 and Z2 in this case. Let's go to the next example. Now, Z2, or Z squared, is 1 plus root 3i. Now, we can do this as long as my complex number is in its polar form. So I need to change 1 plus root 3i into its polar form. And in this case, r would be the square root of 1 squared plus root 3 squared. Of course, remembering our 1 is to root 3 is to 2 triangle. A 30-60 triangle, that of course is equal to 2. And if I was to find the argument, which is the inverse tan of the imaginary bit, root 3 on 1, we'd end up getting 60 degrees or pi on 3. So in this case, 1 plus root 3i is, and z squared, which it equals, is equal to 2 cis pi on 3. Alright. Now, if we apply the roots for this particular equation, the general formula of my root of this equation would be square root of 2, and then cis, okay, pi on 3, divided by 2, and add to that 2 pi k, also on 2, where k is going to be values z 0 and 1, all the way up to n minus 1. N is 2. 2 minus 1 is 1. I'm only going to need 2 roots with k values 0, 0 and 1. What is the first root going to look like? Well, it's a square root of 2. We can't do much of that. Just leave it as root 2. And then cis pi on 3 divided by 2, which is pi on 6. And then 2 pi k divided by 2, where k is 0. That's going to be 0. It's just going to be root 2 cis pi on 6. What's the second root going to be? Z2. Well, it will be root 2 again. And then cis root 3 divided by 2, which is pi on 6. And then we're going to add that to 2 pi k onto where k is equal to 1. That gives us pi. Which is equivalent of root 2 cis 7 pi on 6. And you'll note that the difference between Z1 and Z2, again, if we were to graph them, Z1 and Z2, okay, one would be at 30 degrees and the other would be at 180 degrees away from it. So again, you'd have something like, okay, Z1 might look like this. Okay, that's a distance of root 2. This is Z1. It makes an angle to the positive real axis of pi on 6 or 30 degrees. And the other one is a distance or an angle of pi away from it, 180 degrees. Again, you've got two roots. If you divide 360 divided by 2, you'll find the difference between those two roots. 360 divided by 2 is 180. There's 180 degrees difference, or pi, between our two roots, Z1 and Z2. Lastly, root 2 cis 7 pi and 6 is great, except 7 pi and 6 is not legal. It's too far over our domain. So we should change that into the reverse, which would be negative 5 pi on 6, which we can live with. So our two roots are root 2 cis pi and 6 and root 2 cis negative 5 pi and 6. Finally, this one. So I've got 7 cubed is equal to 8. So we've got some idea that we know what that's going to be already. 2 cubed is 8, but there's actually more solutions that they're going to be. This is z raised to the power 3, so we think there would be 3 values for z that when cubed would equal 8 in this case. Now to start with, 7 cubed is equal to 8 is great, but it would look better if we wrote that as 7 cubed is equal to 8 cis 0. Make sense? It's on the positive real axis. That would mean its argument would be 0. We should write it like that, 8 cis 0. And the rest is just as we did before. We want to find a general value for z. That would be the cube root of 8. And then cis, my angle, which is 0, but divided by n, which is 3. And then 2 pi k, also divided by 3. Where in this case, k will be what values? 0, 1, 2, and up to n minus 1. N is 3, n minus 1 is 2. That's my values for k, 0, 1, and 2. So there's 3 possible values for z in this case. Z1 would be cube root of 8, which is 2, and then cis 0 divided by 3, which is 0, and then 2 pi k divided by 3, where k is 0, that would just be 0. It would be 2 cis 0, which would just look better as 2. Z2, on the other hand, would be square cube root of 8, which is 2 again, and then cis 0 again, but add to that 2 pi k divided by 3. This time k is equal to 1. So that would be 2 pi on 3. 2 pi on 3 in degrees is 120 degrees. Sorry, 2 pi on 3 in degrees is 120. So this would be 2 cis 2 pi on 3. Okay, 2 pi on 3 is legal. It's between our domains, so that one will keep. And the last one, z cubed. So z3 is the cube root of 8, which again is 2 cis 0 plus 2 pi k on 3, when this time k is going to be equal to 2 that will be 4 pi on 3. Now the difference between 2 pi and 3 and 4 pi and 3 is again 2 pi and 3. So again, the difference between each of those 0, 2 pi and 3 and 4 pi and 3 is 2 pi and 3, which is 120 degrees. Think about it. If you take 360 and divide by, this case, 3, because there's 3 possible values for z, it'll tell you how far those roots are stretched apart. This would be 2 cis 4 pi on 3, for which the crowd I know are just going, can't have 4 pi and 3, it's over the limit. We should go 2 cis 4 pi and 3 and come back the other way, which will be negative 2 pi on 3. Now, just to be sure, a little argon diagram as best as we can. The first one, 2 cis 0. So that would be something that looks like this. 2 along the positive real axis. That would be Z1. The second one, Z2, is 2 pi and 3, 120 degrees away from that in a positive clockwise direction or anti-clockwise direction. That would be Z2. The length of it would be 2, and the argument would be 2 pi on 3. The third one is another 2 pi on 3 away from Z2 and also from Z1. So this would be Z3. And I could have got to that by going 2 pi 3 from there, 2 pi on 3 from there, or 2 pi on 3 from there. So either way, Z3 could be 4 pi and 3, not legal, or negative pi and 3, which is the one that we'll use. 3 roots of this equation, 360 or 2 pi divided by 3 gets us 2 pi and 3 or 120. Each of these solutions are separated by that value of the argument, 2 pi and 3 or 120 degrees. There are our 3 roots for this particular complex equation. Z cubed is equal to 8. All right, that's it, girls. I hope you know now what we're talking about when we talk about roots of complex numbers. Thanks for watching. We'll see you later.